Welcome to ZS Circuits Electronic Systems. This is a demonstration of the capabilities of the IoT Power Profiler tool, ZS-2102-A. In this demo, we measure the power profile of a popular Wi-Fi module, powered by two AA batteries. We connect the power profiler in series with the load, and to the PC using a USB cable. Then click on the Connect button. It asks to perform a calibration, which is initiated by disconnecting the load, and pressing the Calibrate button. The calibration process has started, and it takes about 6 seconds to complete. We follow the on-screen instructions. The calibration process is now completed. Let us measure the baseline current. We start and stop the measurement and click on the Estimate button. The tool reports about 120 nanoamps of current without the load, indicating a successful calibration. The tool is all set for capturing. Let us start the capture by clicking on the Start button. The Wi-Fi module is not yet connected to the power profiler. We connect the load now and we see some spikes immediately as it draws current. We notice several transmissions from the module as it connects to an access point. After some time it enters the sleep state. The module is now in the sleep state where it draws few microamps. We will measure this accurately at a later time. The module remains in the sleep state for about 50 seconds, before an internal timer wakes it up. Notice the noisy waveform. This noise is part of any electronic system, and cannot be avoided. But we use this noise to our advantage for better averaging. The power profiler dumps about 8 megabytes of data every second. That's a lot of data to be analyzed. Let us wait for the sleep state to get over. The module comes out of sleep here and we will stop the capture by clicking on the Stop button. We observe that the power profiler has captured about 84 seconds of data, on a 640 megabyte file. The top chart here shows a 1-second window, whereas the middle chart displays a 100 millisecond part of it. Let us set the time scale of the chart to 5 seconds using the scroll wheel. This gives us a better view of the current profile. We use the slider to move forward, and we make some interesting observations. The power to the module is applied at about 9 seconds, and we see some current spikes there. Zooming into that area, we notice some large current spike, which is most likely the inrush current of the input capacitor. Further ahead we observe some strange-looking current profile. Let us zoom into that for more details. On zooming in, we observe the current ramps going from 150 to about 350 milliamps. This is some calibration of the internal power amplifier on the module. The power amplifier is cycled through different power levels, across multiple channels. This is to estimate its nonlinearity, which can be later corrected using some digital algorithms. We slide forward and find some pulses in the waveform. Let us analyze one pulse in detail. We center this pulse and zoom into it. We measure this pulse to be about 390 microseconds wide, and it consumes on an average about 340 milliamps. Note that the rise time of this pulse is only a few microseconds. This shows the response time of the tool. We skip forward and find some receive state of the module with some digital activity. The graph shows some noise variance, but this should not impact the average measurements. It consumes about 68 milliamps in this state. Moving ahead, we find that at about 23 seconds, the module enters a sleep state, and the current goes down to few microamps. Let us zoom out to get a better averaging of the sleep current. We move to a quiet zone to avoid any spikes in the current to get better accuracy. We select that span and we measure about 15 microamps of sleep current. A better estimate can be obtained using the start and stop markers, and measuring the current over a larger span. For example, we set the start at 25 seconds, and the stop marker at 26 seconds, and estimate a better average of 14 microamps. Finally, in order to estimate the overall battery life, we need to estimate the average current drawn over the entire profile cycle. We slide over the chart to find out the start and the stop times of this profile. We set the start marker where the power is applied, at about 9 seconds, and the stop marker at the point where the sleep ends, at about 70 seconds. We set the battery capacity to 2500 mAh and click on the Estimate button to compute the average. It takes some time to compute a million samples for every 1 second span. In the meanwhile, let us grab some beer, and discuss some more features of the tool. The retro dial here indicates the current drawn by the module in real time. It also indicates the battery voltage below the dial. The bottom chart shows any digital signal from the module connected to the power profiler for synchronization. This is very useful for DPA attacks on crypto hardware. In the meanwhile, the tool has finished the computation of battery life. Let us analyze the results. On an average, the module with this firmware consumes about 15 mA from the battery. With a 2500 mAh capacity, this module would run for about 6.5 days. It shows a peak of 1.2 amps, but this is most likely the input capacitor in rush current, and can be ignored for most purposes. Some additional features of the tool include storing the data to a binary file, and loading a file for data analysis. It also supports exporting the data to an XML file. There is also a setting for the data write mode. The buffered mode, which is the default mode, dumps the data to the memory and periodically writes to the hard disk. The HDD mode streams the data directly to the disk without using the RAM. This is suited for solid-state drives. The memory mode dumps all the data to the memory directly and finally writes to the disk at the end of the capture. This is suited for systems with large RAM sizes. Summarizing the performance of the tool, we observe that it can measure currents from few microamps to hundreds of milliamps using a single measurement range. There is no relay switching or load tripping. The maximum voltage drop on the load is well within 100 mV at all times. It can respond to pulses which are few microseconds wide, and measure them accurate to 1 microsecond. The power profiler can store the data directly to the hard disk, and there is no capture length limitation. The current profile, which can be measured by this tool, cannot be performed by any multimeter or an oscilloscope. Most multimeters cannot respond to fast pulses, and oscilloscopes do not have the required dynamic range and have memory length limitations. Also, these can be very expensive to buy, and bulky for mass deployment. The ZS-2102-A comes in a compact USB-powered solution, with a nifty software with lifetime updates and technical support. Order your power profiler at anglercircuits.com. First 100 orders get a $100 discount along with free shipping. We thank you for your interest in the IoT Power Profiler tool.